Welcome to our project presentation. We have chosen the topic Designing a Low-Cost Wind Energy System for a Canadian Single Family to Reduce Their Electric Bill. I am Rinma Shakur Kundu and with my friend Chaudhry Mohammad Abdullah Mahmood will present our research works. We would like to thank Dr. Ashraf Ali Khan for his valuable support and guidance. Our main objective for choosing this topic is to design a renewable energy based power generation system. We would like to combine this system with on-grid power supply. We are looking forward to reduce the grid dependency for a Canadian family as well as reduce their electricity bill. And we are also interested to generate clean energy, and that's why we are depending on renewable energy resources. There are different sources of renewable energy around the world. There's solar, wind, hydro, and biomass, and so on. Among all, wind energy seems to be most suitable resource of energy for our project. Why we have chosen wind energy system? We all know St. John's is the second windiest province in Canada. It is one of the windiest city in the world as well. It's also true that wind energy is carbon free and there is no fuel cost included with this type of energy generation. And we also know that it includes low operating cost and it reduces grid dependency as well. Being a windiest province, as we all know, wind flows almost in same speed all over the year in St. John's. So we can expect longer sustainability from this type of energy generation system. As we are also planning to place this system in a remote location so we can get good source of energy from this type of resources, and this project is also convenient for remote location. At first, we need to select the site for our project. We all know this plays a crucial role in the financial return of the project. If we select an inappropriate site, we might jeopardize the benefit of the project. We have chosen a remote location situated in the Signal Hill Road, which is in the southeast part of St. John's, and that's a coastal region. There is a benefit for choosing this site. Coastal wind projects can contribute to increase the installation capacity and they ensure frequent and powerful winds. We all know, as a remote location, there is no nearby obstacle that will cause turbulence and the disruption in the airflow, and that will be beneficial for our power generation. The height of the tower will be comparatively less as the site is located in higher elevation and there is no obstacle. So we can get fluent wind flow and that will be helpful for our project as well. Here is a bar chart where we can find the average wind speed of our desired location for different months of a year. We can see the annual average wind speed of our location is 7.78 meter per second, which is ideal for setting up a small scale wind turbine system. We can also see that this wind speed increases in January, February, and in the month of November and December, where our energy consumption increases for the winter season. So, this wind generation system can generate more energy at that time, and that will be helpful to meet up our excess demand. Here's the research methodology of our project. At the right side, we can see an algorithm which depicts the pathway for optimizing our whole system. We have done basic optimization using Homer Pro optimization tool. We have used MATLAB Simulink for dynamic simulation and observed the system output at varying site condition. We have also introduced a PID controller to demonstrate the system control and the protection of the whole system. As we have previously told, our main focus is to reduce the electricity bill and we have targeted at least 70%. And we have also targeted to reduce the capital and operation and maintenance cost with maximum utilization of our available resources. At first, we need to find out the total consumption of our desired remote house. At the right side, we can see different kind of appliances which we use in our daily life. We have calculated the consumption of different appliances at that house, and we have tried to find out the total load of that house. We have followed this formula to estimate the load, where we can find the total wattage hour is equals to number of electrical appliances multiplied by their operational hour and the total wattage of these appliances. After that, we need to select the wind turbine for our project. For this operation, at first we need to calculate the total power. For this, we are considering air density, the blade shift area of the wind turbine, the blade radius, and the wind speed of that area. And we are following this equation to calculate the wind power. After the calculation of the available power, we will solve the actual power output of the turbine by following this equation. We also need to calculate the actual output power by considering the factors which are tower height, side shear factor, and Weibull probability distribution that will help us to select the proper wind turbine for our project. We are considering batteries for our project. Though our system is grid connected, there may be some natural disaster or some malfunction from the wind turbine or at the grid. To continue seamless power delivery, we are considering batteries with the system. To sizing the batteries, we have to calculate the total battery bank capacity. For this reason, we are multiplying the total wattage hour and the number of the days for which we are considering the backup. We are considering the depth of discharge as well as the temperature effect for our batteries too. After that, we are calculating the total ampere hour of the battery. For this, we have to divide the total battery bank capacity with the rated voltage of the selected batteries. And then we have to count the total number of the batteries we are selecting. By following these equations, now we have to calculate the battery for our project in different steps. At first, we have considered the daily consumption of our remote house is 16.35 kilowatt as we are taking the backup for a day. So considering the depth of discharge for the lithium ion batteries 80%, we can find the total kilowatt is 20.43. Then we are considering the temperature effect. At the right side, there is a chart where we can find the temperature factor for the lithium ion batteries. At 25 degrees Celsius, the temperature factor is 1.01. So the capacity of the battery system will be 20.64 kilowatt hour. Then we have to calculate the ampere hour of the battery system. As our system is of 24 volt, so we have to divide the result of the step 4, that is 20.64 kilowatt, with total volt, and we can find the ampere hour for system, that is 860 ampere. In step 6, we need to identify the number of the batteries which we need to back up our system. If we consider a 110 ampere lithium ion battery for our system, and as our total consumption is 860 ampere hour and our system is of 24 volt, so we need 8 batteries to back up our whole system. Considering the load demand of the residents and the approximate emergency days, we have chosen the battery named Enersys PowerSave. The nominal capacity of this battery is 6.46 kilowatt hour. As this battery is of 12 volt, so we have connected two 12 volt batteries in series to meet up with 24-volt system. That's it from myself. Now I would like to invite Mr. Chaudhry Mohammad Abdullah Mahbub to go through with the calculation and the analysis of this project. Thank you so much.
Hello everyone, this is Chaudhuri Muhammad Abdullah Mahbub. I'm going to conduct the second part of our project presentation. Let's have a look at our required component list. Following the previously described method, we have selected our required components for this project. Obviously, the prime component is wind turbine. We have selected vertical axis wind turbine because it gives the better output at variable wind speed considering our site location. Ultimately, we have chosen one kilowatt wind turbine from Lotus Energy Technology Company Limited, and the model name is ALOS V1. It has a rated capacity of 1 kilowatt, and it is a vertical axis wind turbine. And the maximum capacity of this turbine is 1.5 kilowatt at a rated wind speed of 10.3 meter per second. And to achieve that, suggest to keep a half height that is 9.90 meter. And the turbine has a lifetime of 20 years. We also need an inverter, and so that we have selected one 3.1 kilowatt 24 volt DC to AC inverter, and we have calculated it as per the peak load. We also have a charge controller and battery system. The capacity of battery is 6.46 kilowatt hour, and it is a 12-volt battery. We have used Homer Pro and MATLAB Simulink for system optimization and simulation. For optimizing the system, firstly, we downloaded wind resource data and inserted per hour load consumption of our selected house. Then we have selected the components to meet up the load demand. However, Homer Pro basically used for steady state analysis. At that time, we considered fixed input such as wind speed and pitch angle, and the system dynamic simulation done by MATLAB Simulink at varying wind speed and pitch angle. And from this graph, we can see the daily load profile of our selected house. It shows the variation of load demand in a day. This is the schematic diagram of our system from Homer Pro. The selected house daily load consumption is 16.35 kilowatt hour, having a peak load 3.37 kilowatt. As well as we can see the system has one AC bus and one DC bus. The grid and the wind turbine are directly connected to the AC bus, but the battery is connected to the DC bus. And these two buses are connected through the inverter, which acts as a bus coupler. Let's consider dynamic simulation. In steady-state analysis, we had built a model based on steady-state output, but the actual output will depend on the current site condition, such as wind speed, air density, pitch angle, etc. These variable parameters will change the average output of the wind turbine. Therefore, we have built a wind turbine in MATLAB Simulink and simulated it to figure out the output of a 1 kilowatt wind turbine based on variable site conditions. While deriving the output of the turbine, we put the values of the required parameters and simulated it. After simulation, firstly we got an output of 1005 watt at 10 meter per second wind speed, while the pitch angle is 0.405. So we have varied the wind speed and pitch angle and kept the other two inputs constant, and finally get an output of 533.3 watt at 7.78 meter per second wind speed, while the pitch angle is 0.49. Now let's talk about the control and protection system design. An efficient control system is a vital part to get maximum output from a system. So we designed a control system considering some unusual factors, and those are wind speed, overload, overspeed, over temperature, and over voltage. And these are some of the noticeable protection systems of a wind turbine that has been configured in the control system. The control system is equipped with manufacturing rated parameters. When these parameters exceed the rated value, the PID controller will control the pitch angle, yaw mechanism, or initiate a shutdown command to the turbine. We also considered system malfunction. That means if the controller itself faces any fault, such as a loss of power, loss of sensors, or any other electromagnetic faults, in that situation, the control will instantly initiate an emergency shutdown command to the turbine. A basic diagram of this emergency shutdown circuit is shown in this figure. We have designed a simple PID controller in MATLAB Simulink to demonstrate how it reacts when the input parameters exceed its rated value. Depending upon the requirement, the PID controller monitors the analog parameters from the input terminals. If the parameters exceed its rated or reference value, which has been set in the controller, the output contacts which of the controller activate the signal to the turbine to operate in its desired range. As per the manufacturer rating, voltage source has been given in line and neutral terminals. The number of input and output contacts depends on the specific protection requirements of the customer. As per the diagram, a closed-loop PID controller has been designed in Simulink. The summation block senses both input and output signals. This block continuously monitors the output parameters with its reference value. As per the settings, when the parameters deviate from their original rating, the proportional, integral, and derivative blocks rectify the input value accordingly and provide output signals so that the turbine can operate in its safe range.
This is the PID controller simulation graph. Here, the red line represents the rated voltage and blue line represents the actual voltage. When the generation starts, the actual voltage starts to rise from zero, and after a certain time it crosses the rated voltage, but just for a few moments. Then it starts to fall again and be stable at the rated voltage level. That means the controller reduces the actual voltage by varying the input variables. And controller repeats this process during the whole time of generation to maintain the desired output. This is the optimization result from Homer Pro. As our project lifetime is 20 years, the optimization shows the NPC is $21,907. That includes the turbine, battery storage system, and inverter installation cost. Besides, the operation and maintenance cost and the replacement expenses have also been considered. The levelized cost of energy (LCOE), that is a measure of the average net present cost of electricity generation for a generator over its lifetime. So, the LCE 0.49 is the average generation cost of this wind turbine energy system during 20 years. And the renewable fractions is 77%. That means the 77% of the required energy is covered by the renewable energy sources. This is our final results. From this table, we can find the consumption of this specific house is 5,967.75 kilowatt hour in a year, and the wind turbine generation is 4,634 kilowatt hour per year. As a result, we need to purchase the remaining power from the grid. So, to utilize this scheme, we have to introduce a net metering system, as we will have to use electricity in a bidirectional way, so that we can use electricity from grid when it's needed, and the utility company will charge the customer based on net uses. Finally, in this way, we can offset our electricity bills above 77%, and It's more than our initial target of 70%. We also conducted an economic feasibility analysis of our project. To generate this cash flow diagram, we have considered the installation and maintenance cost of wind turbine and the battery storage system, and the present electricity rate for Enel Hydro. The present energy charge is 12.381 cents per kilowatt hour. The basic customer charge is 15.81 per month and the tax is 15%. So the cash flow diagram shows that the project will reach its equilibrium states after 14 years if they continue saving the electricity bill as per the current rate. Then, for the next 6 years, the customer will manage to access profit from this project. And this analysis is based on steady state because the electricity bill will vary per month and the selected turbine might incur more or less operation and maintenance cost based on its condition. So the mentioned cash flow diagram is dependent on these varying site conditions. Here are some factors those need to consider for better sustainability of this project. Firstly, customer relocation. If there is a possibility for the customer to change his or her location, then this project will not be a suitable choice because it will be only profitable after 14 years. Secondly, accurate load forecasting. Load forecasting is a technique to predict the energy needed to meet the demand and supply equilibrium, and it plays a great significance for the better operation of an energy system. So, proper load forecasting will enhance the system performance. Then, the proper operation and the timely maintenance is another mandatory requirement to get better output from a energy system. And finally, being conscious to keep the operation and maintenance cost within the limit. Otherwise, the project will become economically less viable. That's it for now. Thank you.